What's up guys, and welcome to another Python tutorial. In this tutorial, I'm going to be telling you about Diophantine equations. What you see on the board right now is a standard linear Diophantine equation. Ax plus by is equal to c. This is where a, b, and c are constants, and x and y are interchangeable variables. Now we're going to be looking at a slightly modified version. We're going to be looking at ax plus by plus cz is equal to n. Again, this is where a, b, c, and n are constants, and x, y, z are interchangeable variables. We're going to try to solve this equation and get the value of n to be true by changing x, y, and z. So, let's jump right into the video. Alright, so here's problem 1. Again, this is straight up copied from the PDF, and I'll just read it aloud. Show that it is possible to buy exactly 50 through 55 McNuggets by finding solutions to the Diophantine equation. You can solve this in your head using paper and pencil or writing a program. Of course, we're going to be writing a program. However you choose to solve this problem, list the combinations of 6, 9, and 20 packs of McNuggets you need to buy in order to get each of the exact amounts. Given that it is possible to buy sets of 50 through 55 McNuggets, by combinations of 6, 9, and 20 packs, show that it is possible to buy 56, 57 through 65 McNuggets. In other words, show how given solutions for 50 to 55, one can derive solutions for 56 to 65. So essentially what we're just going to do is take our Diophantine equation, the bigger one, and replace a, b, and c with 6, 9, and 20. And then our target values are going to be looping through these values, and then eventually we can get to these kind of values. So, we're also going to be replacing x, y, and z with the numbers that we need to make the equation true. Alright, so let's get started by defining a function. I'm going to call it problem1, call it whatever, and give it target. This is our target value, and we're going to loop through multiple ones, but I'm going to call it target. And now we need to go through all the combinations of a, b, and c, which is 6, 9, and 20. So for a in range of integer, and we're going to do target divided by 6 plus 1. So we're going to loop through all of the packets of 6. And the reason I do plus 1 is because in case we round down, we want to make sure that we include the extra 1. And now we need to do the same for all of them, except we're going to change the numbers. So divide by 9, which is the next number. And then the final loop is going to be the same, but the last number. So just note that this will be highly inefficient for other programming languages in general, but for our purpose and coding in Python, we can do this. Now we have to check if a multiplied by 6 plus b multiplied by 9 plus c multiplied by 20 is equal to our target value. So now that we've gone through all of the combinations, we can check this. And if there is, we are just going to return a, b, and c. Now, you may think that this is going to stop the function, and there might be more combinations, or if the number gets bigger, we'll get more combinations. But we are just looking for one combination. It could be the first one, could be the last one, of any number. So the return function works for now. Now, we can implement this by creating a for loop. So just for I in range, in range, 50 through 56. We're just gonna print out problem 1 and then pass an I. Now we can run this, and we get all of the combinations 221, 150, 202, 131, 060, and 112 through 50 and 55. So we have 6 combinations, but it works anyway. So on to problem 2, because we have just solved problem 1. Alright, so now we have a new theorem to prove for problem 2. If it is possible to buy x plus 1 through x plus 5 sets of McNuggets for some x, then it is possible to buy any number of McNuggets greater than or equal to x, given that McNuggets come in 6, 9, and 20 packs. So x is going to be 6, of course, because it is our base number. And we have to explain in English why this theorem is true. Alright, so we have proved for 51 through 56 in the previous problem that there are combinations for them. So for the next, all of the next numbers, we have 50 plus 7. We can break up 7 to 50 plus 1 plus 6. So 1 plus 6 is equal to 7. We know there's a combination for 50 plus 1 because that's 51 and we proved that. And then we're just adding another pack of 6. So it still has a combination. And the same thing, 50 plus 8, we break up to 2 and 6. We know there's a combination for 52 and just add another pack. And this keeps going. For 50 plus 13 even, we can have 50 plus 1 plus 6 times 2, which is 6 plus 6. And we're just adding 2 packs of 6 to the 50 plus 1, which we already know has a combination. So that's problem 2. We explained the theorem. We explained why this is true. And now we can move on to problem 3. Alright, so let's have a look at what we'll be doing for problem 3. Also, he's referring to the previous theorem that we just proved in the first line. So, let's read it. Using this theorem, we can write an exhaustive search to find the largest number of McNuggets that cannot be bought in exact quantity. The format of this search should probably follow the outline. Hypothesize possible instances of numbers of McNuggets that cannot be purchased, exactly starting with 1. For each possible instance, called n, test if there exist non-negative integers a, b, and c, such that 6a plus 9b plus 20c is equal to n. That's our Diophantine equation right there. This can be done by looking at all feasible combinations of a, b, and c. If not, if n cannot be bought in exact quantity, save n. When you have found 6 consecutive values of n that in fact pass this test of having an exact solution, the last answer that was saved, not the last value of n that had a solution, is the correct answer, since you know by the theorem that any amount larger can also be bought in exact quantity. So our task is to write an iterative program that finds the largest number of McNuggets that cannot be bought in exact quantity. Your program should print the answer in the following format, where the correct number is provided in place of n. So this is what we'll be returning and printing out. Largest number of McNuggets that cannot be bought in exact quantity, and we'll replace that part. Hint, your program should follow the outline above. Hint, think about what information you will need to keep track of as you loop through possible ways of buying exactly n McNuggets. This will guide you in deciding which state variables you will need to utilize. Alright, so I'm thinking I'm just going to copy and paste this function, the problem1 function, from the problem1 file, because we can use it for the Diophantine equation solving. So I'll modify it, call it Diophantine, and then we're going to keep track of whatever the combinations are. So storage, and then we're going to append. So storage.append a, b, and c, and then in the end we of course have to return storage. Now we can make our problem3 function. So define problem3, and this is essentially going to be a while loop with, we're keeping track of I, and so we'll just define I right now. And then we're going to have this variable called check. Check is going to be increased by 1 every time we have a actual combination. And if we reach greater than or equal to 6, then we can stop. And every time there's not a combination consecutively, we're going to reset check. And then we're just going to have another storage to track all the things that do not have a combination. Now we can do while not check is greater than or equal to 6. We want to check if Diophantine I, and we're going to increase I at the end, is equal to empty, because we are going to be getting an empty list if there's not a combination. Then we want to append, because that is not a combination, and we're going to append it to storage. And then we're going to reset check, like I said. But if there is a combination, then congratulations. Just increase check by 1. And we're automatically going to stop if we have greater than equal, if check is greater than or equal to 6. Now we can increase I by 1 at the end, and that's it. Now we can just return storage, -1, sub -1. This will return the last value of storage, which would be the greatest number. Now let's print it out. So print problem 3. I will format it if it works. I will format it correctly. And look, we get 43. Brilliant. And now we can format it the way he wants us to format it, which would be right over here. Just copy paste that part. And then we're just going to add quotes, close quotes, add the string with that, and then let's print it out, and here we go. Largest number of McNuggets that cannot be bought in exact quantity is 43. And we can test this out with 44. So print Diophantine 44. And yes, we do get combinations. And yeah, you can test it out all the way, but I assure you that is the right answer. And here, I'll do a test for you. 50. We get a combination. All right, that's problem 3 pretty much solved. Let's move on to problem 4. All right, last problem, problem 4. Let's do it. Assume that the variable packages is bound to a tuple length of 3, the values of which specify the sizes of the packages ordered from smallest to largest. Write a program that uses exhaustive search to find the largest number, less than 200, of McNuggets that cannot be bought in exact quantity. We limit the number to be less than 200, although this is an arbitrary choice, because in some cases there is no largest value that cannot be bought in exact quantity, and we don't want to search forever. That makes sense. This part does not apply to us. Have your code print out its result in the following format. And this is what we're going to be printing and returning. Test your program on a variety of choices by changing the value of the packages. Include the case 6920 as well as some other test cases of your own choosing. I'm going to do 6920, but feel free to test it out for yourself. So for the Diophantine part, I feel like we can just copy paste this and make it more usable for like more numbers. So just do that, modify it. So we get x, y, and z as extra parameters. Now we're going to replace 6 with x, 9 with y, 20 with z. And again, the same thing here. And you should notice something. This is our exact Diophantine equation. We're familiar with this from the beginning of the video. So, let's move on. Define problem 4. I can't type. Alright. So, this is going to just, be a typical for loop. So, just for I in range. So we're going to have 200, 0, and then -1. So this is what's called a step. It's an extra parameter in the range function. It's the step you take. So like it would be -1, so you're going downwards. So 200 to 0 to 199, 198. So that's an extra variable. The default is 1. All right. And now we just have to check if we get nothing. So if Diophantine 6, 9, 20 is equal to nothing, then return I. Now this is just very basic and it isn't very optimizable. This is hard-coded. So actually, let's add it in. So we'll just add x, y, and z into problem 4. Replace this with x, y, and z. And yeah, I did forget the target value, which is I. Alright, and now he wants it printed out in this complicated string. So it requires a bit of formatting. Do that real quickly. So just that string. All right, so I have formatted this very long line, so it should give out the correct thing. So now we can print it out. So let's print out problem 4. And I'm going to give it 6, 9, and 20. All right. And here we go. We get 43. I forgot to add a space with and 20. So right here. Let's try that again. All right, now it's in the correct formatting. Yes. All right, that is problem 4. Thank you very much for watching this video. Please subscribe. It really helps me out a ton. And catch you later. Bye.